Okay, picture this. Your GPS just cuts out. Gone. You're completely lost. Or maybe imagine being able to see deep underground, finding valuable stuff, or even dangerous old bombs without digging a single hole. Sounds like sci-fi, right? Well, today we're doing a deep dive into something that's making this real. It's a revolutionary diamond quantum sensor from Fraunhofer IAF. Our mission to really unpack how this tiny, super powerful sensor works, why it's such a huge leap, and explore some of its applications that honestly sound almost unbelievable.
Exactly. And we'll be drawing straight from Fraunhofer IAF's own materials, their info on the diamond quantum sensor, precision magnetometry for diverse applications, plus details they shared at World of Quantum 2025.
Yeah.
We'll see how this isn't just a small improvement. It's actually transforming whole industries.
All right, let's get into the core tech then. So at its heart, it uses these things called nitrogen vacancies, NV centers in diamond. Can you break that down? What are they, and how do they let this sensor pick up such incredibly tiny magnetic fields with, well, so much precision and flexibility?
Absolutely. Yeah. So what makes this diamond-based magnetometer really special, and Dr. Michael Stobbe from Fraunhofer IAF highlighted this, is its native and intuitive functionality. That sounds technical, but what it means is the sensor inherently gets it right. It can measure all the vector components, basically, the direction and strength of the Earth's magnetic field.
Okay.
And it does this under most conditions. See, inside the diamond crystal, these NV centers are naturally lined up in specific ways. The structure means a single sensor chip made from a particular type of diamond can detect the magnetic field in all directions at once.
Ah, so it's kind of built-in intelligence.
Pretty much.
Yeah.
It's a massive step up from older magnetometers, which often needed way more complex setups and fiddling. And, connecting this to the bigger picture, it drastically cuts down on the need for that complex calibration you often face. This opens up a whole new range of uses, really pushing beyond what conventional magnetometers could do. It's a big deal for research and measurement tech.
Right. And speaking of practicalities, the size reduction is just, wow. I read they shrunk it by a factor of 30 in just 1 year.
Yeah.
How big a deal is that, really, compared to where things were? What does that kind of small size actually enable?
Oh, it's huge. A game changer, really. That reduction makes its current size similar to conventional optically pumped gas cell magnetometers, OPMs they call them.
OPMs, okay.
Yeah, and those are already very sensitive, used in things like medical imaging, but they're generally bigger and, well, more cumbersome. So getting that performance in a smaller box, that's a major win. And the amazing part is, even after shrinking it so much, it still has high sensitivity down in the picotesla range.
Picotesla, that's incredibly small.
It is. And Dr. Stobbe mentioned their goal for next year is even more ambitious. Shrink it by a factor of 5 again and boost the sensitivity even further. They're aiming for the sub-picotesla range.
That's pushing the boundaries. You also mentioned it's robust and has a broad measuring range. Does that mean it works in tougher conditions than other sensors? I also saw something about optional water cooling. That seems practical for keeping things stable when it gets rough.
That's a great point. It shows they're thinking about real-world use. The robustness and range do give it advantages. And yeah, the water cooling is an option for ensuring stable, reliable measurements, even if the environment is challenging. It adds flexibility. But they're not just shrinking the docks, They're constantly improving the heart of it, the nitrogen vacancy-doped diamond sensor head itself. They actually grow these special synthetic diamonds right there at the Institute in reactors. Then they precisely zap carbon atoms and replace them with nitrogen to create the quantum bits.
Wow, they grow their own quantum diamonds.
They do. And they're planning to scale up production, too, moving from making these on 2-inch diamond wafers to 4-inch wafers next year. That's heading towards industrial scale.
Okay, so we've got this tiny, super sensitive, robust sensor. What does this actually mean for, people listening? Let's hit the so what. The real world impact sounds pretty incredible.
Right. Let's start with GNSS independent navigation. GNSS is global navigation satellite systems.
Okay.
GPS is the one most people know.
Okay, so navigating without GPS?
Exactly. We rely so much on satellites, but those signals can be jammed, interfered with, or just aren't available everywhere. Think deep canyons, underwater, even inside large buildings.
True.
The Earth's magnetic field, though, it's different. It varies from place to place in predictable ways. These regional differences can be used as an invisible map, as Fraunhofer puts it. This new quantum sensor is precise enough to read that map. It lets you create really detailed magnetic field maps for reliable navigation.
An invisible map. I like that.
Yeah, so it's this autonomous, interference-free way to figure out your position. It can work alongside satellite systems, sure, but the key is it also works without them. Imagine reliable navigation underwater, in canyons, underground, in buildings, or in tunnels, places GPS struggles.
That really is transformative, especially for exploration or maybe autonomous vehicles in tricky spots. Okay, so that's navigation, but then there's geological measurements. That sounds fascinating too.
It really is. This sensor allows for precise, contact-free localization of underground mineral deposits, finding resources without having to dig everywhere.
Contact-free, wow.
And, maybe even more importantly, it can detect unexploded ordnance over large areas. Think old minefields or construction sites, making those areas safer.
That's incredibly valuable. How does it work for geology? Is it the same magnetic map idea?
Sort of, yeah. The principle is similar. The Earth's crust has different materials, and they affect the local magnetic field. So the sensor detects these tiny variations, these magnetic anomalies. Those can be caused by ore deposits or buried metallic objects like old bombs. They collect this data, turn it into magnetic maps, and these maps don't just show where something might be, but can also give clues about its depth, shape, and size. It allows for this really comprehensive and non-invasive exploration, seeing underground without digging.
Non-invasive exploration.
That's powerful. And I think you mentioned a couple of other specialized uses.
That's right, briefly. Things like biochemical analysis of nerve pathways, so potentially medical applications, and also precision measurements in microelectronics, helping test tiny circuits.
So it's really broad.
Extremely broad. The overall impact is, well, it's fundamentally changing how research is done in many areas, and it's a huge step forward for precise, efficient measurement tech.
It's amazing, really. We started just imagining losing GPS or finding buried treasure, and now we see how this tiny diamond sensor makes it possible. Navigating without satellites, uncovering geological secrets, even making places safer. It all comes down to this leap in quantum sensing.
It really does. This deep dive, I think, gives us a real glimpse into a future where we interact with the world using this incredible new level of precision. It's not just about measuring things better. It's genuinely about seeing the world in a fundamentally new way. So it leaves you wondering, doesn't it? What other invisible maps are out there? What other subtle forces could we start to understand, to perceive, with tools like this diamond quantum sensor? What becomes possible when even the most challenging places underwater, underground, become accessible to this kind of precise, interference-free measurement? Makes you think.